Hello, everybody. Welcome to today's current seminar. Today we have two speakers and two talk. First, we have Professor Wei Chai, the Clement Chair Professor in Applied Mathematics at the Southern Methodist University. He has an impressive background with his bachelor's and master's in mathematics from the University of Science and Technology of China and a PhD in Applied Mathematics from Brown University. Before he joined SMU in the fall of 2017, he was an assistant and then associate professor at the University of California at Santa Barbara, and a full professor at the University of North Carolina. Professor Chai's research spans electromagnetic, fluid, and quantum phenomena, with a recent focus on machine learning applications in high-dimensional PDEs and optimal stochastic controls. He has published over 130 research articles, and he is the author of the book Computational Methods for Electromagnetic Phenomena. And he was awarded the Fenkang Prize in Scientific Computing in 2005. Dr. Chai, the floor is yours, so you can start your presentation.
Problem formulation for PDEs and to construct neural networks. And the neural network, actually, the learning process basically enforcing the Martingale properties for the solution. So, okay, let me get started. And so this work is done with my two graduate students, Andrew Her and Daniel Margulis. And so the outline of the talk will be, first of all, I'm going to give a short review about using SDEs, stochastic differential equations, to construct the deep neural networks. There are a few of work in this area, and the key point is that we use SDEs, the diffusion path, to explore the solution domain. And this is very natural, efficient for high dimension problems. And then I will give a short review on the Martingale problem for PDEs. And then I will show you how to use the Martingale property to construct a neural network. And then we'll present some numerical results for PDEs. And then we'll briefly discuss how to use the DeepMartNet for optimal stochastic control problems. And I will end the talk with some remarks on future work. So the ST-based neural networks and the neural network, of course, the equation one, this is very we are looking at the solution in this format. So in traditional finite element method, the unknowns appears as the coefficients of the basis functions. And here the unknowns are the weights and bias in this affine mapping, then this nonlinear activation functions. So the this functional space is different from the traditional finite element method. And of course, that deep learning, the solution, we're trying to use optimization approach to find the parameters, this was thetas. Theta contains all the matrix and the bias vectors. And so then the SDEs and the parabolic equations, there's a famous work by Padu and Peng in 1990, and the solution of equation 2 of this initial value problems, actually is the terminal value problems. The parabolic equation, the solution U, actually is related to this Y and Z. The gradient of U is Z. So this is a forward STE, this is backward STEs, the coefficients appearing in this PDE, sigma and the mu. You can see this formulation is for very general quasi linear PDEs. And so if you have the sigma also depends on the solution, y is u basically. And so this is a very powerful connection. So the solution, so you can either solve equation 2 to get solution of u, or you can solve this STEs with just time matching, like Euler method. So because using this relation, and there are several works by using this connection to build new networks. The first work actually is done by Winan and his student Hang in 2016. So basically, the key point is how the loss function is the terminal condition, the time t. So you discretize the forward backward STEs. Sorry, okay, oops. Discretize the forward and backward STEs, and but here you need the gradient of u, and so in their formulation they use a small neural network to approximate the gradient of u, and then the trainable parameters as the y0. Of course, y0 is what you're trying to find. So this method allows you to get the solution at one point, and so you just minimize this loss function, you get y0, and that's how this called the deep BSDEs. And then there are by Lazy in 2018, and he come up with this very nice idea. Basically, the loss function actually is the mismatch between two Markov chains. So you have this Markov chain Yn here, and then just another random variable defined by Yn plus 1, and then you compare if it's convergent. These two processes should approach to each other. And but later on, actually, we modify this a little bit more, improved. Make sure both Yn and Yn star are Markov chains, and by just this little modification, we can get a half-order convergence and the solution. So this shows you that if you this is the time, this time axis. This is the solution for different time steps, and we can see the this is the solution for 100-dimensional problems, and so you can see the half-order convergence of the solutions. And then there's another work by Jianfeng 2020, and in this case, he actually trying to solve the eigenvalue problems. And so the previous one is initial value problem, and this is the eigenvalue problem. So the eigenvalue problems actually the just this is a psi. Of course, it doesn't depend on time. So if you just make this artificial time derivative, this of course is 0. So if you start the initial condition, terminal condition as the eigenfunction, then of course everything this be equivalent. But if initial condition is not the exact solution, the eigenfunction, so suppose it's a new network, and then you will have an error. So the loss function is this error, because this eigenfunction should be a fixed point of the semigroup, and this is what is satisfied by the exact eigenfunctions. And if it's not the exact eigenfunctions, and then you have a non-zero loss function. So you can minimize this. And so this is another work about using the STEs to construct the neural network. So now one approach is a little bit different. we used a Martingale problem formulation of PDEs for boundary value problems. So let's consider this differential operator L. So in this case, we have the second order and first order of the convection and diffusion. So this actually is the generator of this STEs. And then we consider more this boundary value problems. So our PDE actually can have another term, V, and the right hand side F. Both V and the F can depend on solution. And then let's consider the Robin boundary condition because this is more general. The dilution and the Norman, it can be a special case of this Robin case, sort of boundary conditions. So this is a shorthand for V for this guy. Now, for the normal boundary conditions, actually, we have to define reflecting brownian diffusion process. This actually is if X is the process in the interior, which is given by the generator I just mentioned, but at the boundary you have to reflect like this. The detail and we'll skip, but basically this reflected process and the before the reflection should satisfy this Scalar-Hall equations, and this is the local time of the process near the boundary, and the local time actually can be computed by this formula proposed by Levy. Is basically you take the neighborhood epsilon share of the boundary, and you compute the occupation time inside the layer. Then you just let epsilon go to 0, and that's actually how you compute the local time. We have some results separated for this, and okay. So now let's see how I can derive the Martingale formulation for this boundary value problems. So let me still denote the reflected process as X, just for simplicity of notation. And actually, this reflected diffusion process is a semi-Martingale. Now, for semi-Martingale, we have the Ito formula. The Ito formula basically is the chain rule. If U is the solution of the PDE, then du, and then you have du dx and the dx. That's the first term. But for the Ito formula, you have to do tile expansion to second term. So this dt actually comes from the dx squared. Dx squared is dt. And this actually from the dx squared, because A is sigma times sigma. So this is diffusion coefficients. So now, if you we put the dx, this ST for the reflective Brown motion, this Scalar equation I mentioned before here. If you take this one, then you can get this term. You get this term, and this second order term and the first order term from this dx will combine into this generator L, the differential operator. Okay, and this term comes from dx. There's a dbt here, so it comes here. Okay, so you have a partial u partial x here. So now this term actually is very important. This term actually is the Martingale, the blue term. So now this is a very important term. Now we use the PDE. LU equals right hand side minus the V term. So this is a very important. This is where we use the PDE. Okay. So now this is a boundary term. That's just the boundary condition we use here. The Robin boundary condition. The derivative is G minus CU. So now, like I mentioned, that this is a Martingale. So now if you integrate on both sides, this is Ito integral, which is Martingale, is this one. Now that tells me if you define ux minus ux0, because you integrate this difference, and this integral of this one f minus v, and the integral of this term, the boundary term, and this whole thing is defined as a MTU. It's the quantity which will be martingale. This is the martingale. The blue term is a martingale. So therefore, the MTU is so defined is a martingale. So now this is the quantity we're going to use to build our loss function. Okay, and we use the martingale property of MTU to build the loss function. And okay, now the fact that this martingale is actually the probabilistic weak form of the PDE. It actually, let me talk about that next. So for the dilution problem, this martingale can be simplified because this is if this tau d, if tau d is the exit time, and actually tau d is also the minimum of the local time being positive. The local time actually is always zero, only it become has an increment when it hits the boundary. So before it hit the boundary, this tau d should be this local time should be zero. So you have this formulation, this and this are equivalent. So if this is true, then this martingale is simplified. You don't have the boundary term. Okay, you have just PDE term here, f minus v. So this is the martingale for division problem. It's simplified. If you take the expectation on both sides, you'll recover the Fermat-Castle formula for the solution at x. And so you can see that the Fermat-Castle formula is a very special case. It's just the expectation of this martingale. Now, this Fermat-Castle formula, actually, you can use the Fermat-Castle formula to find the solution for the Robin problems. In the Robin problem, the Fermat-Castle formula is a bit more involved. You have if you have like mixed boundary condition, you have deletion data, you have Neumann data, you have Robin data. Then this Fermat-Castle formula will have three terms: phi1, phi2, phi3. But this one, you're going to use the local time as the measure, and this is just the expectation and the exit time. Here's the boundary, and this is the gauge from the this C here. Okay, and actually we had this recent results using this formula to compute the electric impeded tomography problems, because here you only need the local solution and electrodes. So actually this is the potential we can calculate use this Fermat-Castle formula. You can see get very good accuracy. And later on in the future work, we're going to use this to combine with Martingale the new network, because we need the path. So now here, let me summarize the importance of the Martingale. There's a Martingale problem formulation for boundary weighted problem. There's an equivalence between these two weak forms. This one, the second one is of course of a classical weak form, the division by parts. The PDE solution is the classical weak form for PDE solutions. If you take test function from this space, and this is a joint operator of the generator. And the probabilistic weak form basically means that if this is a Martingale, that's the probabilistic weak form. And there's work showing that these two weak forms actually are equivalent. The equivalence between the probabilistic weak form and the classic weak form has been established for the Schrödinger operator for the Newman boundary condition by Xu in 1984, and by Vasily Papanicolaou 1990 for the Robin problems. Both actually are former students of Kyla Jung at Stanford. So they established this equivalence of these two weak forms. Now, let's construct our Martingale DeepMartNet. And so this is definition of Martingale. So Martingale basically, so it's a stochastic process. It models a fair game casino. That means the house and the gambler have the 50-50 equal chance of winning. So that means if you have money at the next time, if MS is the of the money you have the time S, when you enter the casino, when you come out the little time T, the average of your money should be the same. So this is the key definition of Martingale. And so that means for any subset of A from the sigma algebra Fs, Fs is the condition determined by the Ms. So if you given the condition at the time S, then this condition expectation should be Ms. But because A is belongs to Fs, so this condition expectation is same. Okay, because MS is A measurable. Okay, so therefore, if you take the left and right hand side, you have this condition. So it's 38. Now this basically translates into the integral of these two process. These two random variable integrate over A. For any A should be 0. So this is a condition we're going to use to enforce in the loss function. So let's see how we do that. Okay, so let's see how we can construct the Martingale loss. So let's first describe the time. Capital T, you pick up a capital T, how long you run the path. So for distribution problem, you have to pick the capital T big enough so the path will hit the boundary most of the time. And you start all the paths from the same point, x0. This is also very important. We only need the path from starting from 1 point. And that will be enough to find the solution. So now we'll have m paths, which is generated by the Euler method. And so this is just you run the Euler method, you got m paths. And so now this is the increment of the process MT from TK TI to TKI plus K. Usually we just take K equals 1. So from TI from TI plus 1. And so the increment will be just U or increment over these 2 times. And the integral originates from 0 to T. Now because the difference is just integral from TI to TI plus K. And this one you just use the Trapezoidal rule to discretize it. And because LU use the PDE, LU is F minus V. That's very important. So this is how you define Martingale. So LU should be F minus V. Now, if for the distribution problem, you have to take the smallest time between the time and the exit time. And this is just a Martingale. If we do this, take the smallest time. So this, if we did if both time bigger than tau exit time, this will be 0. But in general, you just have this one. So that's actually how it looks like. So you this is the time, and this is supposed to start. This is your domain, your solution domain. So you start from x0, you run the path. So you have n paths. So now if so we want this to be approximately 0. So the loss function basically just for each I, you just look at the you want this to be 0, so the square of this. So you take the square of the expectation, and the expectation, of course, just the use this path to calculate, use the sample average. So you take a mini batch AI, which is a subset of this path, and so in principle, you have to take all the subsets because the Martingale property is true for any subset. This should be a conditional expectation. It should be A here. Okay, here. Okay, let me right here. This should be
conditional. Conditional.
Yeah, conditional. Yes, this should be an A here. Okay. Good, Georgie, you're not sleeping. Good. So, so that's why you have this A here, okay? And so you take this condition, then you just use ensemble average, just sum them up. So this is the loss function. It's very simple, and also, so we just in principle you have to loop over the mini batch as you train. Okay, you can pick up one AI, you train the loss for a while, then switch to another mini batch. So you can see that the enforcing the Martingale property deep learning is a perfect marriage. So it just looks like the deep learning is designed for enforcing the Martingale property.
Wei, what is a typical value of n? How many AIs you need to condition upon?
Yeah, actually, in our simulation, we just take I 1,000, and this M is like 10,000 paths.
Okay.
And it turns out it's good enough. And mathematically, of course, in the definition, you should this should be true for any AI, right? But in computation, we don't have to do that. So this is the Martingale for the Robin problem. The loss is the same thing. Okay, so in this case, we have some extra term. We have yeah, this is Robin condition. So you have this one, and so let me continue. So this is for eigenvalue problem, which will be exactly the same. So the eigenvalue problem, the right hand side just lambda u. You said fu. So the Martingale loss just lambda u minus v with this one. And then this is a Martingale loss for the loss function for the eigenvalue problems. So the eigenvalue solution is lambda star and the u star. The lambda star and the u theta star is the minimization of this. And we have to put some boundary loss too. Okay, this should also be included for the deletion problem. We have to use a boundary loss for the deletion problem. So let me make some comments about this approach. Like I mentioned, that the the Martingale property, and this deep learning, the training is a perfect marriage, because you pick up some AI, you train it for N2 apple, and you pick another AI, you train NK apple. When at the end, if this become a Martingale, then this becomes the solution. So so you can see that by choosing different AI, you introduce the stochasticity in the gradient. So when we compute the stochastic gradient, everything is natural. It's not artificially like we just drop some terms and add some terms. But here it's required, because Martingale property requires to pick up all the random subsets. And the subsets is selected randomly. So by selecting all the subsets randomly, you actually enforce the Martingale property. It also gives you the stochasticity required for the SGD. And another one, okay, I mentioned that actually Jordi asked a question about the size of the mini batch. The mini batch actually, in principle, you can choose any size mini batch, but we know the background, the underlying expectation is taken with continuous distribution, the transition probability. So that means my discrete sampling cannot be too small, because that we are like, you cannot take just 1 point. The AI just cannot just one sample, because it doesn't mean anything. So we have a lower bound. I just pick some number 25. So this guarantee the expectation you compute with the discrete samples actually corresponding to the continuous the problem. Okay, so now Another comment is that this actually is beyond Fermat-Castle formula. Because Fermat-Castle formula just give you a solution at one point. This is a solution at one point. But actually, this one, if you use the same number of paths from when you compute the solution 1 point, actually you can get a solution for the whole solution. So this DeepMartNet extract more information from the same set of paths. You can get a solution for all the whole domain. It is so far for this numerical result we have so far. And so there's a lot of mathematical analysis can be done here, because what's the equivalence of this, and why this actually is good, is enough. And of course, the like I mentioned, the Fermat-Castle formula is a special case of the you take the expectation over the whole sample space, so you get the Fermat-Castle formula. And the Martingale property is the conditional expectation among all subsets. So therefore, Martingale property, of course, is more powerful. It contains more information. Yeah, the code, of course, is very simple. Like we all know, just define the loss functions and everything's done. And so let's just show some.
Can I ask a question here too? So in the methods that you presented to both Y.E and also Maser-IC, using they use the Feynman-Katz formula, and they had it was of course expensive because you cannot take many steps, right? Every step you pay for it. Here you still have this cost, right? So you cannot do very integration.
It's just first we know the license problem is for the initial value problem. Okay, so you get solution. You cannot expect a solution for the whole space of time domain, and that's what our experience. You actually, let me show you this picture here. Our experience is that in the Ray's formulation, in the Wheelan's formulation, you can only get a solution at 1 point. That's it. Okay.
For I know that, formulation, but I'm talking about the time discretization also of the trajectories.
Time discretization, yeah. This you basically like here you have to. You're right. You have to choose a. First of all, you have to actually the cost is not the issue. Turns out you see you have to choose a capital T, right? Like I said, the capital T should be big enough because we know the Brownian motion is, so you have to have like a square of delta T is the problem size of the domain. Okay. So that's we allowed you to reach the most possible hit boundary, so you can get a boundary condition right. So once you choose a capital T, and then you have to choose this N, of course. So our experience is delta T should be like 0.01. Okay, that's good enough. Okay, so that's to tell you how many time steps you have to do. Does this answer your question?
Yeah, I mean, so it's expensive for long time integration, obviously.
Yeah, the long time is this depends on the size of the domain.
Yeah.
And so your domain is huge, of course. You have to do long time integration. Yes.
Excuse me, quick question. So this is Panos Dinis from Pacific Northwest National Lab. So this time here is just fictitious time, right? It's not. It's just for the trajectory.
Actually, is the time, like I mentioned, you have to. Okay, let me draw the picture.
This is a steady state problem. It's a boundary value problem. The time here is just for the trajectories of the Brownian motion.
Yeah, you have to have enough time to hit this boundary. That's basically because it's time that the exit time. This is domain D, so you actually have the exit time. So each pass terminate exit time, and then yes, this is not. is not fictitious. It is actually the time of the process. But when you take expectation, you take expectation will when you hit the boundary, so you have a physical terminal time. So it is physical here.
So can you go forward to the solution, not to the before the algorithm, when you had the final slide where you were showing how it compares to Feynman-Katz?
Yes. Here.
Yeah, that's the one. Yes. So here, yes. Do you still have to take derivatives of the of U, which is represented by, so U is represented by a network, right?
Yes. Yes.
So
yes.
do you still have to take derivatives?
Yeah, of course.
With respect to X?
Not with respect to X, just with respect to theta, because X is fixed. Okay, this X are fixed. Just the time, the location. You actually, this X, you don't take derivative with respect to X. You just take derivative with theta. This is only the function of theta.
Right, and F is just the right hand side. Right?
The PDE is LU plus VX
is equal to
U
F.
equals to FXU. Yes.
Okay.
Yes.
All right. Okay. Yeah. Okay.
Yeah. So X is all fixed. Okay. You think about the X at one point. Okay. Just you have to take with respect to theta. Yes.
Yeah. Have you seen the work from? I'll put it in the chat.
Okay.
That was using the Feynman-Katz formula to avoid having to take derivatives with respect to space. It's for the, here you say you use it also for the Robin condition. That paper is for the Dirichlet problem only. But yeah, I'll put it in the chat.
Thank you. But here we don't have to take the respect to X. X is just a sample point, so it's
right.
It's prescribed when before you define the loss function, the X has been fixed. Yeah.
But you say that you still can get solutions for the whole domain.
Yeah, I'll show you. Yes, because this solution is defined by network, right? So once you get a theta, then you just the function is defined for every X.
Exactly. Okay. But okay. All right. Thanks.
Yeah, because the theta is only the unknown in the expression, right?
Yeah.
We try to optimize.
Yeah. So you found numerically that even if you use the data paths from
I'm going to talk about right now.
If you, if you use paths just from one point, they're enough to accurate solution for the whole domain.
Yeah. Yes. I'm doing right now.
Okay. All right. Thank you. Thanks.
Yeah. So this is a numeric result. So this actually is a kind of surprising to us too, because I thought we only can get solution near the starting point, but actually we can get solution all the domains. So that's why I was saying the Martingale property can extract much more information about the solution than the Feynman-Katz formula.
Okay,
so this
thank you.
Take this example, the Poisson-Boltzmann equation. And so this is just some of trigonometry findings. So this is high dimension solutions. So this is the division problem. So this is the loss function. So actually, for this one, we have the Feynman-Katz formula. We can just use the solution to put another constraint. But if you don't use it. We also have that result. And so this is the 20 dimension. And so this is 20 dimension. So you get a solution along the one of the coordinates. This is the whole domain, and this is along the diagonal. And this is the, so if it's also actually this one shows you that if you starting point at a different 3 points, different starting point, you get same solution. So the this also actually we compare. This is a 100 dimension solution. So this is along one of the coordinates. This is along the diagonal. this error is like the second digit, 10 to minus 2. Okay, right here. And
Wei, I think I asked you about this before, but
yeah,
it seems that the boundaries, is that the boundary at the
yes, this is a boundary. And yeah, actually, you go very good question. In 100 dimension, we saw the solution at the unit ball. The reason we didn't, the one before is in the cubic, the 20 dimension, and this is the cubic. Because if we do 100 dimension in the cubic, the diagonal is huge, right? That means that capital T has to be very large. Okay, so we kind of take the easy path out here. So the high dimension problem, the unit ball is easier than cube, because the diagonal of the cube is square root d, right? So if d is large, then you have to run a longer passes. Yes. Also, you can see the okay. So now the eigenvalue problems, this focal Planck equation. So this is not Hermitian problems. So we define the generator. Use this one. Okay. Then so you have a drift. You have a diffusion for the process. And so this part is the generator part. This part is this I call V, and this is the F part. And so you see, this is just a loss function, and the eigenvalue just another variable. So you just minimize this loss function. So let's see how it looks like for the eigenvalues. So this is 5 dimension. Sorry, the eigenvalue in this case is a 5, and it's starting the error. This eigenvalue is like a very big error. They start quickly. You catch up to the 5. And this is the eigenfunction. See, we can get the eigenfunction in the whole domain. The eigenfunction, you have exact eigenfunction, so you can, it's a Gaussian, so you can get it. And this is 25. Again, in this case, the exact eigenvalue is 25. So about 5,000 apples, the eigenvalue has to be captured very nicely. So this is the error of the eigenvalue, I'm sorry. And this is the eigenfunction. This is 50 dimension. Again, the eigenvalue in this case is 50. So you can catch the eigenvalue about 5,000 training. And this is the eigenvalue, or this is the eigenfunction. This is a 200 dimensional eigenvalue problem. Again, the eigenvalue is 200. So you can see, you can catch the eigenvalues very quickly. And you can start very, initially this eigenvalue is just a random number, basically. It's very big error. And then, but somehow the Martingale laws just brings it to the eigenvalue very quickly. This is the eigenfunction. How much time do I have?
We have like 15 minutes, but we have to leave like 10 minutes for question and answer.
Okay, good. Yeah, I actually I only need 5 minutes, because so let's just because of the optimal control problem, if you have a control on the drift only, there's a very nice theory developed by Davis from Berkeley, 1979, around that time. Actually, this optimal control, this is cost function. If you have feedback, the cost depends on the state of the system, and this is the terminal cost. Then the optimal control problem, you just find the smallest cost, and the total. So you define this this quantity, the value function. You define the value function as the remaining cost, the smallest remaining cost. The remaining cost is just from this current time to future, and this is terminal cost. And then actually you can define a cost process. This cost process actually, I see I use MTU, that this is a Martingale. And so this is just the cost up to time t plus the value function, or value process. So this process will be sub-Martingale. So this is a theory by Davis. It says usually this MTU is a super Martingale. It will be a Martingale only if you have an optimal control. So now you can see the optimal control is described by a Martingale. Therefore, our method can be applied to this problem very naturally. Just define the loss function, use the Martingale property. Okay, let me show you. First of all, you will have to know the value function, certify this backward SDE. And then this one, we have to use the BSDE theory, this Padu-Peng theory, because this backward SDE, the solution is the same as the solution of this parabolic equation. This H is Hamiltonian of the control problem. So you have to, of course, this where you have to do the minimum of the controls. So therefore, we have two problems. One is solve this Hamilton-Jacobi equation for V. Another one is solve the object control. Both can be done with two martingales like this. So we have one new network for the control. The control is the function of the state. So you just the control u theta t, and then you have another value function network for the value function, and then the loss function will be two loss functions. One is both are from the Martingale property. So this one is from the Martingale property of the control, and this one is the Martingale property of the PDE. It's exact same like we did before, right? So then you just optimize this guy, you can get both the control and both the value function. That's our hope, of course. We have not done implement this yet. Okay, I'd like to comment on one very interesting statement from the Davis' original paper in '79. And this Martingale, his title is Martingale method in stochastic control. And in the conclusion, he has one statement here. He says, this method, the advantage of this method is that it does not lead to any computation technique. Of course, this can be updated now, because now we found a method is perfectly fit for this Martingale, his Martingale problem of this control problem. So the advantage now, we can just change. If we can get the good numerical results, we can just have the opposite statement of his conclusion in his paper. Now, the future work, actually, there are two areas I like to highlight. One is high dimension problems. Now we know high dimension problems. We can use the method to solve many PDE problems, Hamilton-Jacobi equation, Black-Scholes equation, Fokker-Planck equation, and commuter function. This basic Fokker on the transition path theory. This basic Fokker-Planck equation, those boundary weighted problems. And we compute the many electron systems and non-homogeneous operators with like electrons and the magnetic field. And we can do stochastic controls for queuing and communications. And actually, this whole area was by our professor Kushner at Brown. He wrote several books on this. Basically, it's control and drift. And their method usually basically still that time to find difference kind of type of approach. But now we have a perfect method for this problem. And the next one problem, the cost problem is complex geometry problems. For low dimension problems, but this has many applications like the nanoparticles and the biologists. And also, I'd like to mention that the microchip design The microchip designs basically want to solve Poisson equations in very, very complex geometries. They're made with an interconnect, just like the beams in the building and ceiling. But they have millions and billions of interconnected lines. You have to solve Poisson equations in Laplace equations or Max equations in that kind of domain. So this method is very perfect for this kind of geometry because you don't have to discretize the domains. You just have to record it when you hit the boundary, then either you reflect or then you solve. So these are a lot of potentials for this type of problem too. So that's all for my talk. Thanks for your attention. You're muted. You're muted.
Yeah, thank you. Thank you, Professor Childs, for your great presentation. Very interesting topic. We will now open the floor for questions. Please feel free to raise your hand or type your question in the chat, and we'll address them as they come.
So I'm on this iPad, so I can only see one person in my screen. So
I don't know if
okay.
Jerome is. I think Jerome went to. Jerome is interested, but on this topic, but I think he went to the class. Can you explain the sub Martingale and super Martingale property?
Yeah, basically, the only difference is instead of equal sign, you have inequality. It's either bigger or less than. So you have E, the M, T, Fs, and if this is less than MS, this is a super Martingale. Otherwise, it's a sub Martingale.
But this cannot be translated to a loss function, right? Only
that's right. That's exactly. So yeah, that's exactly because the optimal control is a Martingale, so you have to enforce that. So that's the exact point. You can give you a unique solution because once you find this Martingale, then you got the unique solution for the control problem. If you have a unique solution, of course. That's right. You cannot for the super Martingale, you cannot build loss functions. But we use the fact that it is Martingale, so you can use it to build the loss function. Also for the PDE problem, if you have this PDE problem MTU, if U is not the solution of the PDE, that will not be a Martingale. So that's why you can use the Martingale property to find the solution to PDE.
Yeah.
So if you plug a lot of function V into that Martingale, it will not be a Martingale in that formula.
Also, way here, all the equations you're looking at are linear equations. You didn't do like Hamilton-Jacobi.
Oh yeah, you're right. So the solution actually we got some results for the nonlinear Porter-Bowman equation like this, minus U plus sinh U equals F. And we got results for this one last week. I didn't have a chance to put, actually, if you want, actually, I may be able to find my, yeah. We got.
Just tell us what you have to do for if it's non-linear.
You don't have to do anything. That's the beauty of it, because the equation, like I show you, the Martingale is Martingale, the nonlinear part is inside the Martingale, so you don't have to do anything. Just plug into here. Why is this not moving here? Okay, because our problem, my problem was written like this: LU plus V XU gradient U equals to FXU. So I only need this part to be linear. This part can be nonlinear. So I can solve the equation nonlinear in the lower terms, not in the the second order term.
Right, like the Gordon-Klein type.
Yes. Like
Klein.
this one,
Yeah.
the nonlinear bottom equation. This one.
Good.
Okay. Are there any other questions?
And oh yeah, actually, let me show you. We have two preprint on archive. So if people are interested, they can find it. So, yeah, I have another one slide actually. Yeah, those are the so this one is the there's a paper we're about to submit. The first one, the second one is the one we talk about the stochastic control, and
Thank you so much. And thank you, Panos, for putting the paper in the chat. So you can also check the paper in the chat. Thank you for joining us today. Yeah.
Thank you.
I think it's time to close this session.
Wei, you had over 52 people attending your talk, so apparently there is some interest.
Thank you. I think it's because you did a good PR, I guess.
Yeah.
I'll talk to you later.
Yep.
So it's time to close this session. Thank you for joining us today at this time. Following Professor Chai, we'll hear from Dr. Kuangdai Leng. Dr. Kuangdai Leng, are you there?
Yes, I'm here. Can you hear me?
Okay. Yeah.
I
Sure.
can
you
video.
share your screen? Yeah, can you share
Yes,
your screen
sure.
to see if there is any problem?
Okay. Oh, sorry. Sorry, I have to reopen my Zoom for screen sharing. I'm joining in a second.
Okay.
Okay. Cool. Can you see my screen now?
Yes.
Great. Yeah.
Can you put it presentation? Do you have any video to see if it works? Okay. So Dr. Kuangdai Leng is a senior data scientist at the Scientific Machine Learning Group in Scientific Computing Department, STFC, UK. Dr. Leng holds dual doctorates in engineering and geophysics from Tsinghua University and Oxford University, respectively. He took a postdoc position at geology and geophysics, Yale University, and he came back to Oxford as a postdoc in the Department of Earth Sciences. His research has evolved from numerical methods for solving and inverting PDEs in engineering and geophysics, with a focus on the inelastic wave equations in discontinuous and heterogeneous media, to AI applications in science, especially methods and application of physics-informed machine learning. His talk today is titled Zero Coordinate Shift, Whetted Automatic Differentiation for Physics-Informed Operator Learning. So the stage is yours. Now you can start your presentation.
Thank you very much, Nadani. So Nadani has a pretty nice introduction to myself, and I would start my talk with a little bit introduction of my group. So I'm from the Scientific Machine Learning Group in the Scientific Computing Department, STFC. So we're based in the Rossford-Appleton Laboratory. So this is our campus. As you can see here, we have some large-scale facilities. The biggest one you see is the diamond light source, which is for X-ray, and ISIS. This is a neutron and muon source, and CLF is for high energy lasers. So our missions is basically using the modern AI technologies to facilitate the facilities. So for data processing, analysis, for tomography, and for smart control, things like that. And we also do machine learning research, such as surrogate modeling, computer vision, and large language models for science. So this talk is related to the surrogate modeling, apparently. So yeah, the talk is about our recent study on a trick called zero coordinate shift. So we call it a very, very small trick to enhance automatic differentiation for physics-informed operator learning. So apparently, I'm not using so advanced math as Professor Choi used. I would only use high school math. Okay, so it could be easier to understand. So a little bit background. So physics-informed machine learning. I think most of you who's attending the Crunch seminar should be reasonably familiar with PI. So it started from pins. I mean, the modern ones started from pins, but definitely there are some early works. What I like particularly about physics-informed machine learning is its flexibility. So here I have a nice picture from George's talk. So it's basically with physics-informed machine learning, you can basically ignore what you do not know. Like if you don't have the boundary condition, you can still do it, right? But with numerical methods, conventional numerical methods, you have to know everything to run, for instance, run a simulation. So automatic differentiation is very important for physics-informed machine learning. So the automatic differentiation, or AD, is used to compute the output of the network, okay, with respect to the coordinates, okay, so that we got these terms and we can put them into the differential equations, a PDE or SDE or IDE, all these things. Okay, so that's, we have some, but we don't always have to use automatic differentiation. Okay, there are some alternatives like finite difference and analytical differentiation. For instance, in the physics-informed Fourier neural operators, they're using FFT over a periodic spatial dimension. Also, maybe we can completely avoid differentiation by building some of the physics at hard constraints via the designing of the neural network architectures, such as the linear constraint neural networks and imposed Newman and Robin boundary conditions. Okay, but anyway, these alternatives are subject to restrictions. So AD is still the most general way to computing derivatives along with the neural network. So AD, automatic differentiation, or autodiff, it is used also for backpropagation in general deep learning. Okay, this is apparently the main field, the main purpose for autodiff. So let's do a simple comparison. Okay, so backpropagation in general deep learning is trying to compute the derivative with the loose function with neural network weights. While for the coordinate derivatives in physics-informed, we want to compute the derivative of the network output with respect to coordinates. So if we inspect the dimension of the inputs, okay, so the loose function is the scalar valued, so it's 1. But the network weights, we have millions to billions of them. right? So we write it as this derivative as 1 to infinity. Okay, if we consider the physics informed, we have many to many, because this U is a field in pins. And of course, for coordinate derivatives, we definitely need higher orders, but for backpropagation, we only need the first order. So the current AD, which is heavily optimized for this part, we think it may not have been maximally exploited for coordinate derivatives. So this is kind of our starting point. So before I go to our method, I think we probably should look at AD in more detail. So AutoDiff is a pivotal technique behind deep learning. Okay, it's semi-symbolic. So it's symbolic because the chain rule is exactly implemented by the graph. Okay, it's semi-symbolic, not fully symbolic, because you don't finally get analytical expressions, but you can only evaluate the derivatives numerically. So the key concepts here are the computational graph, leaf nodes, and root nodes. So if you look at this very, very simple problem, you have 3 inputs, x1, x2, and x3, which will be the leaf nodes in a graph. And these are the these operations will make some intermediate nodes, and finally they end up with the root node, which is our target D. And here it's a reverse mode graph, so we can do backpropagation or backpropagation of the arrows based on this graph. And finally, we got the derivatives of the roots with respect to leaves. That's the simplest summary of AutoDiff in deep learning. So there are 2 modes here, okay, depending on in which direction the computational graph is built, okay. So we have the forward mode and we have the reverse mode. So in the forward mode, the computational graph is built from leaves to roots, while in the reverse mode is from roots to leaves. And most importantly, they have different in-graph factorization. So in the forward mode, you always only have 1 leaf, okay, and you have many roots vectorized inside the groove, inside the graph. And in reverse mode, you have many leaves, but only have 1 root. So they are very efficient for the case you have many outputs, 1 input, and 1 output, and many inputs. As you can see here, most majority of the deep learning tasks in this style. So those function with respect to neural network weights. So as a result, the development of reverse mode is much mature. Okay, one big problem with forward mode is lasting. So you have to have lasted forward mode to compute higher order derivatives, and currently it is supported by JAX, but not by TensorFlow and PyTorch. But the key problem is that there's no fast way for general infinity to infinity derivative. Okay, so here these slides show how we do that recently. So in short answer is by combining the for loop and the VMAP. VMAP is basically data vectorization. I'm not going to the details here, and here we take a torch function, for example, but the key information here is if you really want to maximize the utilization of the most powerful reverse, most AD, you need to have a single root. Okay, otherwise you need to either use a for loop or data vectorization. Both would, I would say, heavily impair the efficiency of reverse mode AD. So how about AD for physics informed? Let's start with the single with a simple case of pins. Consider we have a pointwise pins with n collocation point sampled from the domain. So the pins can be write as in this very simple format. So this theta is the network weights. You put the 1 coordinate and you get 1 field, right? So it's very, very simple. But this is what we want is a derivative. Okay, ignore the higher orders. We just talk about first order. if you consider this as a general infinity, this would be very slow, right? And we can't train pins, but in fact, we can train pins, for instance, with DeepXDE. So luckily, we have the trick of root summation. So because you see this is a pointwise mapping, meaning that we can simply take a summation of the output. So doing this like that. So we have only round root. The reason is pretty straightforward to see, because this U1 and U2, they do not depend on xj. Only uj depends on xj. Okay. So this is equivalent to like taking the vector in the VJP, vector Jacobian product, as filled this vector with ones. Okay, so this is too detailed. So my conclusion here is currently the pins have made most of the reverse mode AD. So let's consider operator learning like DeepOLEDs. So here I'm talking about all the, so here I'm using the PINOs, the physics-informed neural operators, but there's a side note, it's not specifically for the physics-informed Fourier neural operators, because these authors also call their neural network PINOs. But otherwise, I think I need some terms for that, so I still use PINOs. So if we consider a PINO like that, compared to pins, it has one more dimension, which is this pi, or the I dimension. It's the dimension of material, dimension of physical parameters. They can be material properties, external sources, initial or boundary conditions, or some observations at some random sensors. Okay, so we have n points and m functions or physical m sets of physical parameters. So essentially, what differentiate operators from pins is the generalizability over this dimension of parameters. Okay, and in our context, it degenerates to a pin when you have only one parameter, so fixed parameter. So there is no straightforward way to compute the derivative of the output with respect to the coordinates. Okay, by the way, we don't sum over the indices, so Einstein summation is not used. So you can see, because the presence of the I dimension, the root summation fails. So what we have done so far is we have two workarounds. The first is we can take a function loop over the first dimension, the dimension of functions. So in that way, we treat the panel as m individual pins. Okay, so here, if you say we take a loop over the function dimension, then we can take summation over the j, and the denominator becomes a single scalar. So we can use reverse mode AD for that purpose. And the example of that is aligned operator learning in DeepXDE. Unfortunately, if we do that, because of this full loop, the computational graph for the final backpropagation will be duplicated by m times, and they will be connected at the root end, right? Can you imagine? Because we have a loop over the we have a loop over the roots. So another way of doing that is data vectorization. So what you do is you duplicate the physical parameters along the point dimension, and at the same time you duplicate the coordinates along the parameter dimension. And in that way, you make this operator pointwise. You see the all the parameters here, they have the same indices, ij. Okay, so by making the pointwise, then you can simply sum over this uij to do the differentiation, right? But in this way, the graph will be expanded by m times at the leaf end, because here you duplicate the coordinates by m times. So zero coordinate shift. So we want to compute the derivative of uij with respect to xj in a loop and duplication free using reverse mode AD. So here I emphasize reverse mode because we need the higher order derivatives. So the concept here is actually very, very simple. As I mentioned, it's high school math. So consider you have a function like that. Okay. How you compute the gradient at this x1? Okay, by definition, you would take a very small infinitesimal increment, delta x1, and then move this point here, and you have another increment on the y, and you divide them and take this delta x1 to 0, right? That's the definition of gradient, very simple. So on the other point, you can do the same, right? So why I'm showing this? Because here we have two increments, x1 and x2, and this corresponds to the case where we send in both x1 and x2 as the leaf variables to the forward path to construct the computational graph. This is what we normally do. So we in our method, we introduce a dummy variable z here and net it to be 0. So you can see these two functions are exactly the same because z is 0. But what makes difference? It will make a difference when we do differentiation. Here we take an increment on delta z. Here we do not add this increment to x, but I add this increment to the dummy variable z. Of course, it is 0 valued. And for the second point, I'm doing the same. Okay, using the same increment conceptually. So here we have only one increment. This means that in AD, z, which equals 0, will be the only leaf variable fed to the forward path. And here I'm showing 2 points. Of course, this z can be shared by millions of points. So geometrically, this delta z means a 0 valued shift applied to all the coordinates. So this is why we name our method as 0 coordinate shift.
I have a question.
Yes, please.
So the value of delta z affects accuracy?
The value of what?
Yeah, of delta z.
Oh, no, we don't use that. It's just a concept.
I see.
There's no delta z in the algorithm.
There's no actual value. I see.
Yeah, that's just a. So it's basically here we introducing 0. So this
helps you. Sorry, it helps you for the indexing, right? I mean, this whole thing is about arranging the indices.
No, it's not about arrange indexing. It's about using something that is not indexed. Okay, let me explain in this.
Okay.
So we have a panel like that with the I for the parameter dimension and j for the coordinate dimension. Then we introduce a 0 valued. It's just one single scalar. Okay, and we add this one single scalar to all the coordinates here. Okay, so because z is 0, here the uij and vij, they are actually the same. The values, their values are the same. So it is easy to prove our central theorem. It's like the derivative of this uij with respect to xj equals to the derivative of this vij with respect to z evaluated at z equals 0. So the concept is exactly the same here, right? But this theorem is very easy to prove.
Can I ask a quick clarification question? So in this case, can that z be vector valued?
It doesn't make sense to have z being vector valued. It is for instance, for 2D problem, you will have two scalars.
Right.
The key point is have a single value z.
Okay, I see.
So,
right.
So because this xj is vector valued, right? Because the coordinates are vector valued. What we want to do is we want to have a single scalar to be shared by all the coordinates. And in that way, we turn this infinity to infinity derivative to infinity to 1.
I'm still confusing in the sense that xj is a vector, isn't it?
I'm saying xj is a vector because the j is index. So it's x1, x2, x3, x4, right?
Oh, so I see. So component-wise addition.
Oh, here I'm not putting component here. Sorry. I'm just demonstrate this in the 1D case.
Okay, if xj is a vector, then how do you define vector addition scalar? Then z has to be a vector.
Oh no, we just this is it in the index form, right? So
then component wise addition then.
It's you can consider for any I and j, for any j, I'm applying the same scalar.
Right, then if that is the case, then this has to be done for all of the indices.
Yeah, exactly.
Okay, gotcha.
Exactly.
All right, thank you.
But it is a single scalar to be differentiated with.
Right, just a partial differentiation.
Yeah, yes. As you can see here, here you only take derivative with respect to the single scalar. But
okay, gotcha.
This d will be duplicated along the z dimension and added to the vector.
Okay, thank you.
If you have 1,000 point, it will be duplicated by 1,000 times, but they are the same. They refer to the same physical variable. Okay.
So hey, Kuangdai, this is just a question here. So why not vectorize over indices j of the x? That will also give the one leaf.
Vectorize what?
Vectorize over j index actually, like VMAP using VMAP.
Here
so
is
that will also.
Sorry.
That will also give you one leaf in that case also.
Here I'm talking about leaf is not about one variable or scalar vector valued variable. I'm talking the numbers, like in how many numbers. Even you vectorize them, it is still a vector, right?
Yeah, exactly. So if you take the derivative of f with respect to, let's just suppose for 1x and then vectorize over all the j indexes. So in that case also you have a single leaf.
I'm not sure it's a single leaf, right? It's kind of a single node, but also with many variables, right? Because you put all the coordinates, you feed all the coordinates.
No, I'm not feeding all the coordinate. I'm just vectorizing over. So I have a closure. I have a closure for 1x, and I'm vectorizing that closure over all the index of the j. So in that case, also you have only one leaf.
Oh, you mean like the scalar?
Exactly.
Right. So yeah, but it's a technical trick. It's not a theoretical trick, right? You always, when you do vectorization, you always pay for especially for the memory when you do, right? Because in that case, you have to duplicate. I missed this part in the previous slide.
No. Yeah, actually, I think there I don't have to pay for the memory, because for this compilation, it's based on the shape, not on the every time you compile. It doesn't mean that it has to fetch the value every time. So the shape is fixed. So it's not exactly technical trait actually.
Okay, so yeah, basically, the key point here is that this C can be shared by the function dimension. Okay, in that case, let me explain later with a graph. So
okay, sure.
Yeah, so basically, this trick is like the zero value trick is kind of I was inspired from IML problem where we want to prove this inequality, and they apply the same value to all the x. Okay, so so in the previous slide we turned the derivative from infinity to 1, and now we want to flip it, so to 1 to a infinity. Okay, how we do that? We introduce an arbitrary valued dummy tensor Aij here. So Aij can be any value. Okay, and we contract it with our network output. And finally, we factorize the wanted derivative, which is infinity to infinity, to two parts. First, we compute a scalar to scalar, which is 1 to 1. And then this will give us another scalar. And taking the scalar as root, we get it 1 to a infinity. Okay. So, and we have some other properties, and I think I will skip them. So, so maybe I think it's better to talk for better understanding. We have this very simple code. So if how to implement this on burgers. So for the burgers, we have 2 dimensions, right? It's X, time, and space. So we will define 2 scalars. As you can see in the PyTorch code, I just defined 2 scalars, which are both 0. Okay. And then we apply these scalars to the vectors. So this t and x are basically the vectors containing the t and x for all the collocation points. So it doesn't change their values because both these 2 scalars are simply, zeros. And we require but the only difference here is they require gradients. They are differentiable. And getting the t and x, we can send them to the neural network, okay, or sending them to the trunklet of the dipollet. So if you look at here, this part, the forward pass is exactly the same as before, as if you are not using this trig, right? So the only difference is if you're not using this trig, here t and x are both vector valued, and these vector valued things will be all they will be all differentiable. They are all leaf variables. But with t and x, we have that. So next, and I think the vectorization on this has been implemented in PyTorch and TensorFlow other than, right? Otherwise, it would be very expensive to compute. Then we define a tensor, an arbitrarily valued tensor with the same shape as U, and do the contraction to get our omega. Okay, so note that the burgers has not been used so far. Okay, so what we do here is we get the scalar valued root omega, and we can take derivative with the scalar valued ZCS variables. So we have ZT and ZS as we defined both zeros, and we get these derivatives like omega t, omega x, omega xx, and then we combine them in a scalar as scalars based on the differential equation. So here I'm combining this term and the last term because they are both linear terms, and then take derivative with respect to aij, and finally we got the ux. Finally we got the linear part, and then we take the omega x with respect to aij, we get the ux. And then based on the equation, we find the Burger's equation. Okay, but this can be, for instance, on the framework I will show later in our implementation for DeepXDE, this process can be completely hidden from users. So the property is that DCS can be very memory and time efficient.
Excuse me, Kuangdai, this is Lulu. Can you go back by one slide? I just small details I'm looking. If you go to the code page.
Which?
The code, the PyTorch code. The previous page. Yeah.
This one?
Oh no, I just put in your slide is fine. Just the previous page of the.
Oh, slide. Oh, sorry.
Yeah.
Yes.
Yes. So here the linear is equal to grad OT minus VOX. This is which OT is the derivative of U to T, right?
No, the OT is derivative of omega.
Oh, omega to Z.
To ZT. So this is a scalar. And we minus the second derivative of omega to X. And this V is basically this viscosity. And this part is a scalar.
Yes.
And then we take derivative with respect to A.
Oh, I see.
You get the linear part, this one minus this one. And then you do the nonlinear part and combine them.
Okay, I see. Got it. Thank you.
Here I'm using here because I'm trying to emphasize, like if you have 2 linear terms, you can do only one derivative with respect to A. Anyway, which is not a very big deal.
Okay.
Yeah. So the key thing is I will show in the example, the computational graph in this case for neural operator or for DeepMartNet can remain as large as the graph for the corresponding pin, meaning that where m equals 1, because it does not duplicate the computational graph on the root side or on the leaf side. Okay, and it is agnostic to forward pass, meaning that it has a lower, it is at a lower level than the neural network, so it does not change anything what is happening here, like the changed data, architecture, or point sampling, and does not affect the training results. Okay, very quickly for the experiments. So we have a scaling analysis for this linear PDE. Okay, so we consider the number of functions or number of physical parameters, a number of collocation points, and here P is maximum differential order in this equation. Okay, and we compare compare our implementation with the two existing operators in DeepXDE. One is the operator Cartesian product, and one is PD operator. So I name them respectively as function loop and data vectorization. This is basically what's happening inside these operators. So the function loop is basically, as I introduced before, we take a loop over the m function, and data vector is we duplicate parameter along point dimension and duplicate point coordinates along parameter dimensions. Okay. So this is the most important figure in this experiment. So it shows that the GPU memory almost remains constant as we change the number of functions for DCS, while for the existing operators, they scale with the function. And this clearly shows that in the other two workaround approaches, the computational graph has been duplicated, and the reason is very clear. Okay, and the scaling behavior with respect to n is basically all the methods scales linearly with the number of collocation points. No problem with that.
Can you quickly explain what y-axis represent?
Oh, x.
Y-axis.
Oh, y. So sorry, the left is GPU memory.
Okay, gotcha.
For training the neural networks. And
so
x is number of functions, and this is basically wall clock time.
I see. So the left figure, y-axis represents the GPU memory in gigabyte.
Yes. Yeah, in gigabyte.
Okay, thank you.
Yeah. So
hello, Kuangdai.
Yeah.
So this is based on PyTorch, right?
I will show later, like all the backends are pretty much behave the same.
Oh, great. Thank you.
Yeah. So there's a very interesting thing is the scaling behavior with respect to the PDE order. Let's go back to the PDE. It's basically the maximum order here. Please note that the x-axis is linear and y is logarithm. So you can see both the memory and the time increase very fast with order of the PDE, right? ZCS, our algorithm, cannot remedy this scalability, but it can push the orders all the way up to 9 on the single 80 gigabyte GPU. So for the other two, it just stopped at about 4. Okay, so then we try this method on a few operators at different scales. So we solve these PDEs only with physics, without data, right? But adding the data loss won't change the measurements too much because the data loss is very simple. It doesn't touch outgrand. So we have 3 problems: reaction diffusion, burgers, and creature of love. Okay, these are 2 second order. This is up to the 4th order. And this one is actually the demonstration problem in DeepXDE. So we compare the three methods. So here this column shows the memory actually occupied by the computational graph of backpropagation. So you can notice here, okay, so the memory for these 2 methods are mostly like m times larger than DCS, indicating that DCS do not duplicate the computational graph. Okay, and the reason I have explained it is that the Z variable, they are shared by the points, but they are also shared by the functions, by the ith dimension. Okay, and because of these big savings on the computational graph, we also can save the war time a lot for calculating the PDE loss and for backpropagation. And the accuracy is almost not affected. There are some randomness here, right? Because the arrangement is different, you can't get exactly the same accuracy. So this is an intuitive comparison for the fourth order PDE with 10,000 points. And you can see it's basically a intuitive view of how much you can probably save from the algorithm. So so for now, I would quickly take over with our new repository. Is about the implementation of DCS in DeepXDE. So this is not implementation of DeepXDE, it's just a very simple extension you see with only 5 Python files, right? So it's very small. And to use this DCS, we have 2 steps. First, you replace the classes, okay, with our classes, with our new classes. That's the first step, so which should be straightforward. And second, you change the PDE to DCS format. We have tools to do that. So this is original PDE typically looks like. This is for the diffusion reaction equation, and it will be changed into this style. You can read the details here, but what I want to emphasize is these changes are really minimal. So with these 2 changes, you'll be able, so the examples are provided. If you have a DeepXD running, the newest 1.10 running, so you can easily install these, and these are the measurements we get, okay, for all these. So basically, PyTorch is pretty much similar. We're very similar to Pando. While TensorFlow is a little bit different, okay, because DeepXD is using JIT compiled TensorFlow. So for TensorFlow, we get less savings on time, but more savings on memory because our code is not JIT compiled.
Can I ask a quick question here?
Yeah.
Kuangdai? So have you tried with the JAX? Because the JAX provide quite a useful mechanism with the vectorizing the functions. It seems that it is called, I think, the VMAP.
Yes, VMAP is data vectorization. So I tried JAX actually with our own code. So from a depot-led from scratch with JAX, and JAX gave the maximum savings. But we're not doing here because, so from our own experiments, JAX benefit most from DCS. But in DeepXDE, JAX is not supported for DeepMartNet. So this is why it is not here.
I see, very interesting.
Okay.
All right, thank you.
So the VMAP I would mention is VMAP is, I would strongly, I mean, someone may be different from, disagree with me. VMAP is not a theoretical optimization. Okay, VMAP is kind of algorithmic. So, okay, finally, I would emphasize our paper and the repository, our nice implementation focus on DeepXD and DeepMartNet. The algorithms itself is not difficult to implement if you have some operators in PyTorch, for instance. So finally, some discussions, limitation. So we have implemented DCS also for convolutional neural networks and FNOs. So these are not pointwise neural networks. These are based on a structured grade. Okay, so we found that DCS can make autodiff faster, but the performance is still cannot beat finite difference and analytical differentiation. Okay, so for example, the FFT based, differentiation in F nodes. Okay, I think this is so technically speaking, I think this is not a limitation of DCS itself, but we have the pointwise panels. Like we do not take advantage of structured work grade, right, in a pointwise panel when the grade is actually available. So the further step is what we're trying to do is, as I said, we benefit from sharing this D across the function dimension. So we can avoid duplicating the computational graph, either from root or from leaf. So we're trying to also share this with the dimension of networks, because we can train many networks at the same time, either for smaller operators for a big problem, or the same operators with different model initializations. So if we train more networks sharing the single variable, so this could probably give us more benefit. So in conclusion, so the derivative with respect to coordinates in physics-informed operator learning has a special structure which can be exploited to maximize the most powerful reverse mode AD. So our trick is by theoretically factorizing this derivative into two parts. Both has a single root, so we can use reverse mode AD. And the key is that this trick can maintain the physical size of the computational graph at the pins level, which means the number of functions or parameters equals to 1. Hence, we observe an order of magnitude performance boost in both memory and time. And this method does not affect the training result, so it has nothing to do with the architecture or point sampling or things like that. So yeah, that's my talk. I'm happy to answer any questions. Thanks.
Thank you so much for your great presentation. Very interesting. So now we open the floor for questions. Are there any questions from the audience for the speaker?
Can I ask a quick one first?
Mm-hmm.
Sure.
So yeah, first of all, thank you very much for a very interesting talk, because I and Raj and George somehow worked on the automatic differentiation looking at this perspective, and we found that utilizing JAX actually brings a tremendous speed up in this regard. So that I wonder, how do you implement JAX in this part? Because it seems I'm still a little bit confused about the part where you mentioned that JAX is the one that you bring the most speed up in this case. And it seems like to me that VMAP is exactly vectorizing the thing is exactly what you explained here, so that I kind of lost in that part how, okay, first of all, how do you implement this in JAX? Then what speed up have you observed is something I'd like to ask.
Yeah, I totally understand. So it's basically, I only have these slides on the PyTorch, right? So it's basically what I'm trying to say here is if you have many roots, okay, if you have many roots, so you can specify for the Jack ref, because it's reverse mode, so you can only have one root. And if you have 100 roots, and if you do chunk size equals 1, then the loop will be, then you will have for loop over the 100 roots, no problem. And if you use a larger, like 20, so on this root, so it will make 5 chunks, and each with 20 roots vectorized by VMAP. But if you run that on PyTorch, you will find your memory also expand for 20 times, because it will actually make 20 copies of NN graph. This is PyTorch behavior. Okay. And
yeah, here there is a, why do you using the Jack rib? It is a full Jacobian.
No, I mean, I'm just talking about here is like, how do you compute a general infinity to infinity derivative?
Yeah, exactly. So that's my point. So you don't compute using Jack reverse. You use JVP and then compose it with the unitary vector. So we never compute the full Jacobian by any method.
I know your point. I know your point.
Yes.
Here, what I'm trying to, the information I'm trying to deliver here is VMAP, at least in PyTorch behavior, in PyTorch, this VMAP will make multiple memories, will require multiple memories. Okay.
Because you are computing the full Jacobian. That is the reason.
No. Yeah. It's probably the reason. Okay, this is probably the reason. So back to the JAX problem. Okay, so we use JAX. The baseline, okay, the baseline we use is here. Okay, the grant. It's like how the DeepXD is doing with JAX.
Not exactly, because if you see that, like, it's very hard to understand that why the graphs are being duplicated.
Okay, in our case, as I say here, there's so if you look at, please let me go to here. Okay, so this is the operator. We add this z to this, right? So in this figure, we show that this delta z or z as a leaf variable is shared by all the points, x1, x2, x3. And here, what's different here is if we add a single scalar value z here, this z will also be shared by the function dimension. Okay, so we don't.
So I can explain that how VMAP works actually. So let me tell you that how VMAP works. So first of all, in JAX, the data structure is not the contiguous data structure, it's called pi tree. And according to that, the graph is computed. So you write a function which takes only one input, and that is a closure. And that closure, you again compose with VMAP. VMAP is a function. And that when you compose that, then you just apply that on a certain axis of the data structure. When you have a partial u ij and over partial xj. So I assume is the batch size. So you compute partial uj by partial xj, and for m you can just vectorize, and it will never duplicate the graph. It will never retrace the graph. So that is like what we did the exercise. If you remember in KTH also, I showed you this thing. So
okay, so I think we could probably arrange another meeting to look into what we're doing in detail.
Exactly.
But so I'm telling you, like my baseline for benchmarking JAX, okay, is using basically what DeepXD does currently, right? Just taking the summation of the root. So here.
I think Lulu can comment on that, on the DeepXD part. That
right.
I think
I use
anyway. Yeah. I think in DeepXD also, if you duplicate the graph, it gives the warning. That much I know. But I think Lulu can comment on that.
No, I mean, it's not, sorry, it's not duplicate the graph, right? It's just, for instance, if you use the function loop, if you take a loop over the function dimension, it will create for each time, for I equals 1, for I equals 2, for each time it will create a graph, okay, at the pin scale. And this graph will be connected by the final loss function. When you take the mean square error of this vector, they will be connected at the end. That's what I mean, duplication. It's not actually duplication in a programming sense, but just compared to the, here I'm referring to the graph of a pin. So meaning that in this case, the graph size will be m times larger than that for m equals 1. Okay, I'm happy to look at more in depth with the JAX problem, but based on we don't use VMAP, we just use the summation of the root, the grant function in JAX to compute the derivatives, and if we apply this, you get a very big savings, but we're not implemented it nicely in DeepXD because it's not supported.
Yeah,
Okay.
also just a last comment. When
Yeah.
the slide you showed with the torch.jackreb, I think you can replace, you can use the here GVP, JVP or VJP,
Yeah,
and
yeah,
then
yeah, sure.
yeah,
Well, we never use the full
yeah,
Jacobian.
So yeah, so if you use that, then your memory will come down to just by factor of n. So that's why you are getting that much. You are having the memory overhead by that factor. So you can just use the JVP.
So we never use jackref. I'm just here explaining what happens if we want infinity, full infinity to infinity Jacobian. Okay, so our baseline, we're very careful with when you report in experiments, like how much you based. So we are to start from the solid. All these measurements are based on the current 1.10 DeepXD. Okay, so if you say I'm not starting from the right, so you can talk more to Lulu.
Yeah. So for this case, for PyTorch or TensorFlow, so it's kind of in DeepXD, as you mentioned, we have jacks for pings, but we do not have jacks for deep physics informed DeepMartNet yet. Yeah, for these results, I think it seems good to me because usually when I run this physics informed DeepMartNet, for example, 1 GB memory is very common. So here, if we have the memory 0.02 GB, it's surprising to me.
Yeah, you can. I think it's pretty easy. I think for you as an author, you can pretty much replicate the results in the repository in 5 minutes.
Yeah, but I'm not sure about jacks for physics from DeepMartNet. I haven't done that yet.
Okay. Yeah. So it's basically for these baselines. So it's DeepMartNet. It use the summation of roots for all the backends. Definitely not using jackref. Yeah.
Yeah, thank you. Thanks for your interesting talk. Thanks.
And there was another.
Yeah. Shanyan Mao, can you can you introduce yourself first and then ask the question?
My question is exactly the same as previous question, so I have no more question.
Okay. Great.
Oh, but yeah, you also do a lot of jacks. Did you do jacks for physics from DeepMartNet?
Yes, I just coded, right? Just coded and do a benchmark, but never solve any problem. Right. So yeah, it's not difficult, right? It's not difficult. JAX is very, very powerful.
Okay, are there any other questions?
Yeah, I have a proposal since all friends here. Maybe Lulu and Raj and Kuangdai could benchmark exactly the same case in terms of memory and accuracy and also, let's say, the Bergers, your middle benchmark that you have here. You already have it, and do it in JAX. All 3 different implementations in JAX, and see what you get, because it seems to me your gains are spectacular. So but you know, the implementation details are important. So Lulu, what do you think? It's worth doing this exercise?
Yes. Yeah. I think for physics for DeepMartNet, JAX is the only missing part contained in DeepXD. Yeah, happy to do that.
Yeah. But also benchmark the individual implementations.
Yes, sure.
Versus, I mean, it seems that Raj is doing something different from you, Kuangdai. So then it will be nice to see the pros and the cons. Not to be antagonistic. Say we want, since you're working with the same stuff, we want to learn from you. And
yeah, sure. Yeah. So this is why I'm still kind of like contacting you and Lulu and Raj say say we could kind of be agree on like what we do and how we sort of making this, usable for the users, and I'm happy to show a kind of but as Raj said, maybe I'm not using checks at the correct baseline. But here now what I have obtained is that with the other three backends, you can very easy to reproduce these one order of magnitude improvements.
Yeah, but even the PyTorch version, the most frequent complaint I hear from everybody here on the ground is that they run out of memory. So I don't know if it's a excuse or it's true, but that's what I hear. So I can understand, and Lulu is right. The 0.02 versus 1 gigabyte, that's huge.
Yeah. I think if you're happy, I can try to arrange a bunch of people together. Like we talk more detail.
I think the three of you, Lulu and Raj and you and whoever else wants to join, but definitely the three of you should communicate. And as I said, I ideally would like to see the benchmark. Just like you have, your benchmarks were beautiful, very clear. The explanation was clear. It's just one more point of view or two more points of view.
Yeah.
If I may say something, did you try using, for example, Navier-Stokes? Because in the JAX, I think they say that when you use the JBP, you gain velocity with the number of inputs is greater, significantly greater than the number of outputs. And in all the cases that I assume that you have a single output, right?
Single output. Oh yeah.
For example,
so here we have here we have a like vector, scalar valued. The reason we doing this is because we want to show like we do not affect accuracy, right? And with training without data to get the good measurements. Navier-Stokes we have implemented, but for no matter with hours or without hours, we can't get to a good accuracy or reasonable accuracy without data. That's why we're not presenting it here.
Oh, okay, I see.
Yeah, so for Navier-Stokes, it's a nonlinear problem, and it's a vector valued output. It's more complicated. Lots of complications here, there in the physics. So without data, you can't get to like less than 20%.
But in that case, what about another type of system? Because as I said, like in the documentation for JAX, they say that their JBP works better if the number of outputs is significantly greater than the number of inputs. And actually, if you play it, then you observe that. So
yeah, that's also a good point. It's like, I'm exploring the forward mode. Okay, forward mode is basically JBP. So currently, because our method, if I go to earlier slide, it is very, very friendly to just take the first step. You have a one single leaf instead of like, but we turn it down for the first study, for the first paper, is because TensorFlow, PyTorch, they do not support nested forward mode. That's the current status.
Okay.
So meaning that if you're using TensorFlow or PyTorch, you can only solve first order ODEs.
Okay, got it. Thank you.
Yeah.
A great talk, by the way.
Thank you, Hoon.
Are there any other questions?
Here I just have one comment. So TensorFlow has supported this forward mode computation with the gradient.
Sorry?
TensorFlow supports JBP computation now.
Which one?
TensorFlow.
Yeah. Okay.
There's there's one official implementation And there's another unofficial implementation which I found really useful.
No, it does support. I know it support forward. I mean, nested forward. So forward, inside forward.
Yeah, I think this part you can search. I think some data and we observed that from TensorFlow website, but just a quick comment. So no question.
Okay. It's not official right now, right? You mean?
It is, but
okay, it is. Okay.
Yeah.
I tried it like for 3 or 4 months ago. It says you can do first order, but you can't do second order forward.
Yeah. TensorFlow always has this kind of a
yeah. Deep learning, develops very fast. Yeah.
Any questions? Yeah, I cannot see any raised hand here. So I think it's time to close the session.
Yeah.
Thank you, Dr. Leng, for your great talk. And we hope everybody found this session informative and inspiring. Thank you all for joining us, and we look forward to seeing you next week. Have a great weekend. Thank you for joining us today, Dr. Leng.
Thank you. Thank you for the invitation. Bye-bye.
Bye.